So hello, now it's 3 o'clock in Germany and we will start now. I hope that some attendees will join in later. Ladies and gentlemen, I would like to welcome you on behalf of Bruker Optics to our today's webinar. The topic is the world's first FTIR spectrometer technology capable of covering the far and mid-infrared in a single scan. My name is Matthias Kessler and I will chair this webinar. I'm chemist and application scientist at Bruker for the mid-infrared R&D product line. Our speaker today is Dr. Hja Stammer. She holds a PhD in physical chemistry and is an expert in surface modification and functionalization. She earned her PhD at the Ruhr University in Bochum and worked during her studies in close collaboration with the Karlsruhe Institute of Technology in southern Germany. Later she joined the research team of Professor Wöll at this recognized institute and for her postdoctoral studies. At Bruker Optics, she is responsible for high-end research applications like FTIR spectroscopy in ultra-high vacuum and for the VERTEX Spectrometer series. I want to give you some additional information regarding the course of this webinar. It will be structured into two parts. At first, the presentation part of approximately 30 minutes and later on a discussion part where we can answer your questions in detail with a duration of approximately 15 minutes. During the presentation, you can use the WebEx question and answer functions to send your questions to me and they will be collected for the discussion part. We also provide the possibility to answer your additional questions via email if the time is not sufficient to cover all of your questions. After this more technical information, I want to hand over to Hja and we will start with the presentation.
Hello everybody. Thank you very much for the introduction, Matthias. So then let's start with the guideline at first for this webinar. I think most of you have heard about the VERTEX FM functionality. We have introduced this unique functionality for the research level spectrometer VERTEX and VERTEX 70V at the beginning of last year. And we say it makes an FTIR dream of most spectroscopists to become a reality. Why do we say that? As you know, the standard mid-infrared spectroscopy can provide a spectral range from 4 or 6,000 down to 400 wave numbers due to the limitation of some mirror window materials, especially the beam splitter material and the detector, and sometimes also the light source. And if you want to get more information from the far infrared region below 400 wave number, you will have to start your measurement for the reference and your sample in the mid-infrared region at first. Then stop the measurement, open your spectrometer, exchange the beam splitter, and normally also the detector or even the light source. And then close the spectrometer, wait until it stabilizes again, and start the same measurement for reference and for the sample again in the far infrared region. That will cost a lot of time. Well, it is possible now using the unique VERTEX FM functionality to do this without any need to change optical components and cover the entire mid-infrared to far infrared or terahertz region. That means from 6,000 down to 50 wave number in one single data acquisition. Well, and in this webinar, I want to start with a few application examples using VERTEX FM functionality to show you the additional value of this functionality in many application fields and industry sectors. And after that, I want to give you some detailed specifications of the VERTEX FM optical components and want to give you some recommendation of the spectrometer system configuration. At the end, maybe some of you have already asked, well, you talked about VERTEX 70 and 70V spectrometer. What is about the high-end product VERTEX 80 and 80V spectrometer? Is the VERTEX FM also available for that? Or if not, what is the alternative for VERTEX 80 spectrometer? Well, this question will be answered at the end of this webinar also. Okay, first, I want to show you some advantages of the additional far-infrared region in many application fields and industry sectors. So in some inorganic and organometallic substance, we have some characteristic bands in the far-infrared region, and also the lattice vibrations can also be found in the far-infrared region. So that's why in this application field, the VERTEX FM is very important. Also for semiconductor development and research field, and for studies on polymer filler materials and color pigments is VERTEX FM very useful. And geological and rock analysis, for example, where we'll find a lot of additional information in far-infrared region. And pharmaceutical filler materials and active agent measurements can be done in the far and mid-infrared at the same time in one go. And polymorph differentiation or crystallinity identification, for example, plastic explosives can be identified. And at last, in the basic research, low-temperature matrix isolation spectroscopy. Well, in all these application fields, VERTEX FM can make your measurement easier and faster. So maybe you say, well, all these application fields are so abstract. So that's why I want to name you a few industrial sectors to give you more idea where in VERTEX FM can be used. Not only in the basic research fields, but also in the pharmacy, in mining, or semiconductor industry, in security, and in building industry to identify the building materials, or, of course, in polymer industry. So, and in the following, I will show you application examples in these 4 fields. Let's start with the first one. For inorganic minerals, carbonates as an example, what you see here is the far-infrared spectrum of calcium carbonate, and here in the above channel, this black spectrum is the measured ATR raw spectrum with VERTEX 70 and ATR platinum ATR accessory from Bruker, and in the middle, and this is a corrected ATR spectrum. As you know, in ATR spectrum, the relative band intensity and the band position can be shifted and can be different from the normal transmission spectrum. And that's why in the ATR spectrum, this has to be corrected. And this effect of shift and relative intensity difference can be even stronger, much stronger in the far infrared region than in the mid-infrared. That's why the ATR correction is here very important. And what we have done is to use the advanced ATR correction included in the Bruker Opus software function. And we got this curve fit and the single peak positions. And then we create the second derivative of these bands to allow an exact analysis of the absorption bands. And well, you can even find more details of this study in our prepared application note for carbonates minerals study. And we have done the same for 2 other carbonates, as you see here, and analog to above, you have the black spectrum here as raw ATR spectrum measured with VERTEX FM function. as you see, from around 600 down to 30 wave number. And in the middle, you have, again, the ATR corrected spectrum, and the second derivative better showing the peak position. On the right side, you can find a table with all the peak positions of these three carbonates. And in the left column, you have the peak position of the measured ATR spectrum corrected. And on the right side, you have the reference. It is the transmission peak position. And you can see here we have a very good agreement between the corrected ADR measured with VERTEX FM and the data in reference in transmittance. So, in the next example, I will talk about gypsum. Here you see we have measured not only the far infrared region, but the whole MIR and far IR regions from 4,000 down to 30. That means the region below 400 is now available using the VERTEX 70 FM functionality. And you see, now you will not only see the sulfate anneals and crystal water vibration in the mid-infrared region, but also the lattice vibrations as additional information in the far infrared region. And if we now zoom in the far infrared region from 700 to 10 wave number and measure this region with both the internal standard light source globar and the external mercury arc lamp, we'll see, especially below 100 wave number, using the mercury lamp, we can additionally increase the signal-to-noise ratio. You see the red line with the external lamp is more smooth. Well, then let's come to the next example. Here we measured inorganic minerals halides. As you know, if you want to measure such kind of alkali metal halides, some salts, they don't have any signal in the mid-infrared region. But now, with VERTEX FM, you have the additional far infrared region. And as you see, we can distinguish KBR, KCl, and NaCl very clearly. And we repeated the measurement for each substance a few times, and you see the very good reproducibility here. Now, as you know, this kind of halides can be contamination in some medical pills, and so with the VERTEX FM now, you have the possibility to simultaneously identify active agents in the mid-infrared region and the impurities in far infrared region. Well, next topic, polymorphism. I will take that as an example. Maybe you will ask, what is that and why is that so important? So, as we know, the same chemical compounds can have different crystal forms, like crystals, solvates, hydrates, dissolvated solvates, and so on. And these phenomena and these different crystal forms are named polymorphs. Different polymorphs can have very different physical properties, like solubility, melting points, particle size, and so on. And well, normally polymorphs can be characterized and identified with X-ray diffraction method. Also, solid-state NMR and Raman and other TGA methods are used. And now with VERTEX FM, since we have the additional far infrared region, and it makes the characterization of polymorphs with FTIR technique much easier. And this different physical properties of the polymers, they will influence especially the pharmaceutical product development, product manufacturing, quality, and stability. So here with these two pictures, I want to visualize the different crystals of sulfur thiazole. As a good example, you see, here in this case you have some needles, and there are some cubes or tetrahedral, so they are quite different. This is just a microscope picture of the crystal form itself. Well, and of course we have collected more details in our application note, which you can download from our webpage, or you can also contact us via email for this information. And now, in the following 3 slides, I will show you 3 examples of polymorphism or pseudopolymorphism. The first one is lactose with or without H2O crystalline water. So you see, with VERTEX FM, again, you can measure down to the far infrared region. Here we show until 30 wave number, and in the mid-infrared region, you have a difference mainly at 800, or you see some difference in the 1600 region, or here 3500. And in the far infrared region, if you zoom in there between 700 and 50 wave number, you see some additionally difference, especially at 600, it's a dominant difference, or here around 300 or 250. So, and this additional information should be very helpful for you. And the next example is also pseudopolymorphism for theophylline. And, well, let's have a look in the mid-infrared region. Well, you already see some difference here and there. And mainly, it is the NH and OH bands at 2500 and 3500 here. And here, the bands, well, a little bit difficult to distinguish. And go in the far infrared region, we zoom in there, and you can see, well, at 400, this one is definitely only, this band at 400 is definitely only from one polymorph. The last example is the best one, because here we have a real polymorph. Example are these 2 crystal types of sulfur thiazole, and if you look at the mid-infrared region, you can see really no difference. So you see these 2 spectrum just cover each other very well. Maybe only somewhere some relative bands intensity difference, but this is really difficult to calculate. And now we see the real additional value of the VERTEX FM functionality, because the only difference visible is in the FIR region, around 100 wave number, exactly at 130 this band, and 80 wave number. Well, let's come to the next example. In the following 3 slides, I will show you some copolymer filled with some filler material in different concentrations, from 15% filler material concentration down to 10 and even 3%, and how you can measure that with VERTEX FM. So the first one is styrene butadiene copolymer filled with ammonium phosphorus polyphosphate, and the concentration of filler material is 15%. And as you see here below, this black spectrum is the pure polymer matrix itself, only the polymer itself, and then the red one is the polymer together with the filler material, and you see, well, here a mid-infrared region is almost the same, but in the far infrared region you have some difference, and the blue one is now the difference spectrum of the both. If we compare this difference spectrum made with the real IR spectrum of the pure filler material powder, then you can see, well, it can find the bands one after each other, but the dominant difference is still in the far infrared region. Well, let's go to another example with 10% filler material, titanium dioxide in polystyrene. Here you have the same case. First, the polymer matrix, you see, polystyrene, and with filler materials, the difference spectrum show you the difference mainly in the far infrared region, and compared with the filler material spectrum itself, it fits very well. You can identify the filler material as titanium dioxide. Well, what about lower content filler material? Is this technique sensible enough? Now we have another copolymer filled with trioxide. Here, again, the pure polymer, and, well, the difference is smaller polymer with filler. The difference spectrum shows only these three bands, one small one in mid-infrared region and the other two in far infrared, and, well, in comparison with our pure filler material spectrum, we see, well, it can be well identified as antimony trioxide. So, that was the application examples and example spectra. Now I want to introduce you the very new Bruker VERTEX FM ATR library, and which is the first of its art. And it fits very well with the VERTEX FM functionality. Normally, the standard ATR library will give you, provide you a range from 8 or 6,000 down to 400. And, and the VERTEX FM ATR library will collect it with VERTEX FM functionality and goes down to 50 wave number, and or even lower. And here, you can also build up this library or build up your own library with your own samples, and that will help you to identify and classify your polymer, for example, products. Well, and this library is very flexible. I just want to show you with this spectrum search example. So what you see here in red is the spectrum of SB copolymer filled with calcium carbonate. And if you do a spectrum search with the file limits from 4,000 down to 30 wave number, then you find the best match is styrene butadiene. But if you won't find a match for calcium carbonate. But if you do the search with another file limit for the far infrared region, which is now possible with the VERTEX FM ATR library, file limits will be from 600 to 30 wave number, and you'll find the best hit is calcium carbonate. So just a sample how to use this ATR library. And more details, you can find it in our product note for this library. Well, and now I want to go to the specifications of our VERTEX FM system configuration and the key components. So the ultra-wide range beam splitter and the wide range DTGS detector are the key components of VERTEX FM functionality. And with ultra-wide range beam splitter, you can achieve a spectral range from 6,000 to 10 wave number. of course, depending on the other used optical components. The DTGS detector can be used from 12,000 down to 20 wave number. The beam splitter can only be used for vertex 70 and 70V spectrometer series, whereas the detector can not only be used for 70 but also for the 80 series spectrometer. Well, and well, you heard now we talked about the VERTEX FM functionality for the VERTEX 70 purge and VERTEX 70 vacuum spectrometer. Now, what is the difference between purge and vacuum VERTEX FM functionality, and what is the benefit of vacuum spectrometer? So I want to show you this difference with this SB copolymer as an example. So what you see here on the left side, it's this copolymer measured with VERTEX FM purge functionality. On the right side, it is measured with VERTEX FM in a vacuum spectrometer. And, well, on the left side, you see the dark blue spectrum is a single channel measured, and the light blue is the resulting absorbance spectrum. And you see in this absorbance spectrum some noise-like features. And if you compare these noise-like features with the single channel, then you can see these features come from the residue water vapor absorption. And if you look at a vacuum spectrometer result, you can see, well, here and under vacuum, you can achieve a virtually noise-free far infrared THz spectrum. And well, the benefit of vacuum is that the water vapor absorption or other disturbing bands can be just avoided. And in the purge version, you will have to make sure that the measurement condition must be kept the same during the reference and the sample measurement. So, with vacuum version, you have a better performance and higher stability. That is the point. And well, at the end, the VERTEX 70 purge will give you a specified, achievable spectral range from 6,000 to 80 wave number in one go, and VERTEX 70V FM provides you 6,000 to 50 wave number in one go without changes any optical components. So, and I promised you to give you alternative solution for the VERTEX 80 and 80V series spectrometer, and before a few years we have established the automatic beam splitter changer unit for VERTEX 80V spectrometer. And as you see in the product notes here on the right side, it is a mechanical device with 4 parking stations for 4 different beam splitters. Each of them can be automatically via Opus software inserted into the spectrometer interferogram. And of course, everything is full automatically. No venting of the optic bench is necessary. You don't have to break the vacuum if you want to change the spectral range, and save a lot of time and improve your thermal mechanical stability of the measurement. And now you may ask, well, the beam splitter is changed, but what about detector? So we thought about that problem. So we combine the beam splitter changer with an external detector chamber, which you see in this picture. So herewith you can bear up to 5 different detectors, and combined with the 4 different beam splitters, you can automatically cover the complete spectral range from UVVs through NIR, MIR, into far infrared THz range. That means from 50,000 wave number down to 5 wave number using the VERTEX 80V spectrometer. I think this is not only an alternative, but a much better and complete solution for spectral range extension than the VERTEX FM. And here you see an example spectrum showing using the automatic beam splitter change unit. We measured the lactose monohydrate as an example, and using the VERTEX ADV with platinum diamond ATR and 3 different beam splitters. KBR, see here in red, for the mid-infrared and the far infrared multilayer, and 50 micrometer mylar. And well, from 4,000 down to 5 wave number. And well, now only for the far infrared and terahertz range, we have a new solid-state beam splitter for both VERTEX 80 purge spectrometer and vacuum spectrometer. Here you see the product node again, and with this one beam splitter, you can cover the complete far infrared terahertz spectral range, and useful spectral range is from 900 down to 5 wave number. The efficiency below 100 wave number is quite high, and actually that connects perfectly the mid-infrared fingerprint region with the far infrared region, because it goes up to 900 wave number. And if you use a high power mercury lamp and the new wide range DTGS detector, you can cover the complete range from 900 down to 20 wave number with only one single data acquisition. And here you see a small example measured with VERTEX 80 and this solid-state beam splitter, the spectrum showing 700 to 10 wave number. This is the single channel measured using different aperture size. Well, and here I want to summarize again the additional values of the new and unique VERTEX FM functionality. And if you want to know more about this unique function, you can find the application notes, which gives you an overview of the VERTEX FM, and application note dedicated for differentiation and characterization of polymers. Another one dedicated for polymer filler materials, and one for carbonate miners and ATR studies in the far infrared region. And a VERTEX FM brochure is also available. So once again, you can cover the mid and far infrared spectral range in one go, save a lot of time. You can achieve the complete molecular and lattice vibration spectral information. Don't have to break the purge or vacuum condition anymore. And all the wide range optical components are insensitive to humidity. And well, these additional values can be seen in various application fields and industry branches. Want to name them here again. Not only basic research, but also pharmacy, mining, semiconductor industry, security, building materials identification, polymer or art conservation, or even quality control for packing materials. So there we come to the end. I want to thank you all for your attention, and I'm happy to answer your questions.
So thank you, Xia, for the interesting facts and the information you provided to us. Now we have time for several questions, and I want to encourage you all to use the chat functionality or the question and answers and send your questions to me. The first one will be, so there's an existing VERTEX 70 spectrometer with nitrogen purge, And the question is, what is the best time to use for purging to have the best signal to noise you can achieve?
Well, the best time, and this is a good question. The best time, in general, I would say 15 minutes is enough. But well, I must add, this depends on a condition in your lab. And well, the most important thing is the condition during your measurement for your reference and during the measurement for your sample must be the same. So that means you opened the sample compartment, put your reference sample in, and that lasts 10 seconds, and then you close the sample compartment, then wait 15 minutes. But let's say you put your sample into the sample compartment, but you used more than 1 minute, then of course you can't use the same purge time for your sample as for the reference. So you have to play with this purging time, so to achieve the same humidity and atmospheric condition in the sample compartment. So because in the result spectrum, in the absorbance spectrum, this is actually a different spectrum of your sample measurement and your reference measurement. So if the condition or the water contents during these two measurements are different, then you will have you will see the water bands in your result spectrum. So if you played good with this condition, then you can even get noise-free or water vapor absorption-free spectrum in a very in a rainy day, on a rainy day, or in a not air-conditioned lab. So
okay, thank you for the answer. Then we go to the next question, and that is it possible to upgrade an existing system with this functionality, or how is this handled?
You mean, okay, of course. Yes, the answer is yes, you can. If you already have a VERTEX 70 on 70V in your lab and it's a standard one, then you can add this key components for VERTEX FM functionality, which I mentioned. It is just this wide range beam splitter and this wide range DTGS detector. Of course, we also recommend you to add this automatic shutters so that you don't have to change the window materials between the sample compartment and the optics bench. And of course, you will need a good purge kit for the VERTEX 70. So yes, it is upgradable, and if you buy this VERTEX FM functionality together with a new system, we have some additional price reduction packages.
Okay, yeah, that's good to know, this information. And then there's a further question, and it's about the use of an external FIR source, mercury lamp, and if you use this, we have then to switch between this and the internal source, or is there a possibility to have one measurement again for the whole range?
Yes, that's a good question. So we mentioned in one is our slide that the mercury lamp can give you a better signal-to-noise ratio, especially below 100 wave number. And that means, but that doesn't mean that you should switch from the internal source to the external mercury lamp, because the mercury lamp can be used in the spectral range from 4,000 down to 10 wave number. Well, in the case of VERTEX FM, down to 50 wave number. So it can cover the entire mid-infrared and far-infrared region, so you still don't have to change optical components.
Okay, thank you. And then another question would be, is it a big advantage to have a vacuum system with the use of the VERTEX FM functionality?
Well, the biggest advantage of the vacuum system, and as I mentioned in this one slide, is you have a better overall performance and a better stability. So normally, if you use purge system, so we have, as you see in this, if you've seen in this one spectrum, the result is actually satisfying. It's not good. It's not bad. But it will only work that good if you have a good purging. That means you have optimum purge volume and the gas quality. Let's say nitrogen must be good enough. Or if you're using a dry air, the humidity must be very low, and you shouldn't have any impurities in the purging gas. And sometimes you will have some disturbing effect or some defect in your purging, and that will also impact your measurement result. And as I said before, and depend on how long you opened the sample compartment for your reference and your sample, and to exchange the samples, you have to play with the purging time, and this is a feeling and need a lot of experience. But the vacuum system, it will stop this. It will get rid of this problem of the residue water absorption at the very beginning, so you won't have water or CO2 other things at all in your optics bench, in your whole spectrometer. So that makes it much easier. You don't have to worry about that problem anymore. So that is the main benefit, say. And that's why you can also measure further down to the THz region with the vacuum system.
Okay. Now we have one attendee who is asking about the achievable resolution of the wide range beam splitter, and if it's possible to measure a resolution of half wave number.
Well, half wave number is still possible. Well, and the best achievable resolution using this wide range beam splitter is 0.4 wave number, and that is actually more than enough for all condensed phase samples, and also for gas samples under normal pressure.
Okay, thank you. So, are there some additional questions? If so, then please feel to write me. And that seems not to be the case, so we are coming to the end of this webinar. I want to thank you all for your attendance and for your interest, and of course again Dr. Sommer for this interesting facts. I hope you enjoyed the time with us, and I want to encourage you to have a visit on our homepage for further information, and later on this webinar will be available as recording there. And additionally, there will be also dates available for future webinars, and I would appreciate it if you join us again with new exciting topics. So I finally will close this webinar and thank you all again for your attendance. Goodbye.
Goodbye.